A rough budget estimate for a 2 MVA primary service is as follows. The 13.2 kilovolt primary switch estimated cost is $50,000 to $100,000. The transformer, which is 2 MVA, 13.2 kilovolts to 2.4 kilovolts, estimated cost is $100,000 to $200,000. The switchgear at 2.4 kilovolts, estimated cost is $50,000 to $150,000. Additional considerations include site preparation, clearing, leveling, and grading the site for equipment installation. Estimated cost is $10,000 to $50,000. Foundation and supports, concrete or steel supports for equipment. Estimated cost is $10,000 to $50,000. Conduit and wiring, connecting equipment with cables and conduits. Estimated cost is $20,000 to $100,000. Engineering and design professional services for planning, design, and specifications. Estimated cost is $20,000 to $50,000. Contingency fund, allowance for unforeseen expenses. Estimated cost is $50,000 to $100,000. Based on these rough estimates, the total cost for the 2 MVA primary service, excluding the motor drive and low voltage loads, is approximately $240,000 to $650,000. These estimates are approximate and may vary depending on specific project requirements, location, and market conditions. It is recommended to consult with contractors and suppliers for more accurate pricing. The 13.2 kilovolt primary switch serves as the initial point of connection to the utility grid, safeguarding downstream equipment through robust protection mechanisms. The 2 MVA transformer operating at 13.2 kilovolts to 2.4 kilovolts efficiently converts high voltage power to low voltage levels suitable for industrial applications. The 2.4 kilovolt switchgear distributes and controls electrical power while providing essential protection for connected equipment. Site preparation encompasses essential tasks such as clearing vegetation, leveling the ground surface, and ensuring proper grading for equipment installation. Foundation and supports involve the construction of concrete or steel structures designed to provide stable and secure mounting platforms for heavy electrical equipment. Conduit and wiring entail the installation of protective conduits and cables to establish reliable electrical connections between various components of the power system. Engineering and design services encompass professional expertise in planning, designing, and specifying electrical systems to meet specific project requirements and regulatory standards. A contingency fund is established to address unforeseen expenses that may arise during the project, such as unexpected site conditions or equipment modifications. When estimating costs for a 2 MVA primary service, it is crucial to consider various factors that can influence the final budget. Firstly, the cost of the primary switch, typically rated at 13.2 kilovolts, can vary depending on its features, such as low break capability, fault interruption rating, and the inclusion of protective relays. Secondly, the transformer, a critical component for stepping down voltage from 13.2 kilovolts to 2.4 kilovolts, can have a significant impact on the budget. Transformer costs depend on factors such as its kVA rating, insulation type, and efficiency. Thirdly, the 2.4 kilovolt switchgear responsible for distributing power to various loads can vary in cost based on its configuration, number of breakers, and protection features. In addition to these major equipment costs, site preparation is an important consideration. Site preparation involves clearing the land, leveling the ground, and ensuring proper drainage. These activities are necessary to provide a suitable foundation for the electrical equipment. Foundation and support costs cover the construction of concrete pads or steel structures to support the primary switch, transformer, and switchgear. The design and construction of these foundations must comply with local building codes and engineering standards. Conduit and wiring costs include the materials and labor required to install the necessary electrical conduits and cables. These conduits and cables connect the primary switch, transformer, switchgear, and various loads. Engineering and design costs cover the professional fees for electrical engineers and designers who develop the system layout, perform calculations, and create detailed drawings. A contingency fund is essential to address unforeseen issues that may arise during the project. These issues could include unexpected site conditions, changes in equipment specifications, or delays in delivery. In summary, a rough budget estimate for a 2 MVA primary service should include costs for the primary switch, transformer, switchgear, site preparation, foundations, conduit and wiring, engineering and design, and a contingency fund. Obtaining quotes from multiple vendors and contractors is essential to ensure accurate cost estimates. Furthermore, consulting with experienced electrical engineers and contractors can help identify potential cost savings and optimize the system design. The 13.2 kV primary switch typically includes features like a disconnect switch, circuit breaker, and protective relays to ensure safe and reliable operation. The transformer's impedance, voltage regulation, and cooling method are important factors to consider when selecting a transformer for a specific application. The 2.4 kV switchgear usually includes features such as circuit breakers, metering, and control devices to distribute and protect the electrical system. Site preparation costs can vary significantly depending on the condition of the land. Factors such as the presence of existing structures, soil conditions, and environmental regulations can affect the cost of site preparation. Foundation and support costs depend on the size and weight of the equipment. Foundations must be designed to withstand the loads imposed by the equipment and environmental conditions. Conduit and wiring costs can vary depending on the distance between equipment, the size of the conductors, and the type of conduit used. Engineering and design costs typically range from 5% to 15% of the total project cost. The contingency fund should be sufficient to cover potential cost overruns and unexpected expenses. It is important to document all assumptions and cost estimates in a detailed budget report. The budget report should also include a schedule for the project, identifying key milestones and deadlines. Regular monitoring of the budget and schedule is essential to ensure that the project stays on track. A total cost for a 2 MVA primary service can vary significantly depending on the specific requirements of the project. However, by carefully considering all of the relevant factors and obtaining accurate cost estimates, it is possible to develop a realistic budget. Remember that these figures are estimates, and actual costs may vary. The best approach is to get detailed quotes from suppliers and contractors in Leesburg, Virginia. For the primary switch of 13.2 kV, consider the interrupting rating needed based on the available fault current from the utility. This will impact the cost. For the 2 MVA transformer, look at different insulation types such as mineral oil or dry type. Dry type transformers may be more expensive upfront but can reduce environmental and fire safety concerns. For the 2.4 kV switchgear, consider the level of automation and monitoring required. Advanced protection relays and communication capabilities will add to the cost. In terms of site preparation, geotechnical investigations may be needed to determine soil bearing capacity, which influences foundation design and cost. Also, consider any necessary permits and environmental impact studies. For the foundation, consider using precast concrete to potentially save time and money compared to cast-in-place concrete. For conduit and wiring, consider using aluminum conductors instead of copper, especially for larger sizes, as it can be more cost-effective. For engineering and design, ensure the engineers are familiar with local codes and standards in Leesburg, Virginia. Finally, the contingency fund should be adequate to cover potential delays due to weather, material shortages, or other unforeseen issues. Remember to get multiple quotes for each item to ensure you are getting competitive pricing. Also, consider long lead times for equipment, which can affect project scheduling and costs. Regularly review and update your budget as the project progresses and more information becomes available. First, confirm the utilities requirements for the primary service connection. This may include specific equipment requirements or metering specifications. Second, conduct a thorough site assessment to identify any potential challenges or constraints. Third, engage with qualified electrical contractors and engineers who have experience with similar projects. Fourth, obtain detailed equipment quotes from reputable suppliers. Fifth, Develop a comprehensive project plan that includes a detailed budget, schedule, and risk assessment. 6th, regularly monitor project costs and track progress against the budget and schedule. 7th, maintain open communication with all stakeholders, including the utility contractors and engineers. 8th, be prepared to make adjustments to the budget and schedule as needed. 9th, ensure that all work is performed in accordance with applicable codes and standards. 10th, thoroughly test and commission the primary service before placing it into operation. The transformer's impedance affects the system's fault current levels and coordination of protective devices. Consider energy-efficient transformers to reduce operating costs over the long term. For switchgear, arc flash hazard analysis is crucial for personnel safety. Remote monitoring and control capabilities can improve system reliability and reduce maintenance costs. Investigate potential rebates or incentives from the utility for energy-efficient equipment. Consider future expansion when designing the primary service to avoid costly upgrades later. Proper grounding is essential for electrical safety and equipment protection. Surge protection devices should be installed to protect equipment from voltage transients. Consider the environmental impact of the project and implement sustainable practices where possible. Proper documentation and record keeping are essential for future maintenance and troubleshooting. Training for operating personnel is crucial to ensure safe and reliable operation of the primary service. The voltage drop between the transformer and the motor drive should be minimized to ensure proper motor performance. Harmonics generated by the motor drive can affect the power system's quality and efficiency. Power factor correction may be needed to improve the system's power factor and reduce energy costs. Consider using variable frequency drives VFD to control the motor speed and reduce energy consumption. The motor starting current can cause voltage dips that affect other equipment in the system. Soft starters or auto transformers can be used to reduce the motor's starting current. The motor's insulation class and temperature rise should be appropriate for the operating environment. Regular maintenance and testing of the primary service equipment are essential to ensure its reliability. A preventative maintenance program should be developed and implemented. Spare parts should be readily available to minimize downtime in case of equipment failure. Consider using condition monitoring techniques to detect potential problems before they lead to equipment failure. Thermographic surveys can be used to identify hotspots in electrical equipment. Vibration analysis can be used to detect mechanical problems in rotating equipment. Oil analysis can be used to assess the condition of transformer oil. A detailed commissioning plan should be developed to ensure that the primary service is properly tested and configured before being placed into operation. The commissioning plan should include procedures for testing the primary switch, transformer, switchgear, and protective devices. The commissioning plan should also include procedures for verifying the system's performance under various operating conditions. The commissioning plan should be reviewed and approved by a qualified electrical engineer. A final commissioning report should be prepared documenting the results of the commissioning tests. The commissioning report should be retained for future reference. Periodic inspections of the primary service should be conducted to identify any potential problems. The inspection should be conducted by qualified personnel. A written report should be prepared documenting the findings of the inspections. Any identified problems should be addressed promptly. The primary service should be protected from physical damage. The primary service should be located in a secure area. Primary service should be protected from weather elements. The primary service should be properly ventilated. The primary service should be kept clean and free of debris. The primary service should be properly grounded. The primary service should be properly labeled. The primary service should be properly maintained. The primary service should be properly operated. The primary service should be properly tested. The primary service should be properly inspected. The primary service should be properly protected. The primary service should be properly documented. The primary service should be properly commissioned. The primary service should be properly decommissioned. The primary service should be properly disposed of. The primary service should be properly recycled. The primary service should be properly reused. The primary service should be properly reduced. The primary service should be properly repaired. The primary service should be properly replaced. The primary service should be properly upgraded. The primary service should be properly modernized. The primary service should be properly automated. The primary service should be properly controlled. The primary service should be properly monitored. The primary service should be properly analyzed. The primary service should be properly optimized. The primary service should be properly secured. The primary service should be properly managed. The primary service should be properly planned. The primary service should be properly designed. The primary service should be properly constructed. The primary service should be properly installed. The primary service should be properly connected. The primary service should be properly energized. The primary service should be properly energized. The primary service should be properly isolated. The primary service should be properly locked out. The primary service should be properly tagged out. The primary service should be properly tested. The primary service should be properly inspected. The primary service should be properly protected. The primary service should be properly documented. The primary service should be properly commissioned. The primary service should be properly decommissioned. The primary service should be properly disposed of. The primary service should be properly recycled. The primary service should be properly reused.